Hello students. In the last class, I have discussed various aspects of the cell model. We have learned how cell model was developed, and later on with the help of cell model, we find out the angular momentum spin of the ground state as well as parity of the ground state. And you will observe that maximum time for most of the nuclei, this cell model gives us the correct value of angular momentum, spin and parity. However, there are few exceptions where this cell model fails, but you can observe that most of the time it will provide us the correct value of angular momentum, spin as well as parity. Now question arises, ground state is okay, but in nuclei, experimentally people find out different excited states also. So apart from the ground state, the nuclear cell structure have various excited states. Like for example, if we consider the example of 8O17, then the ground state is this one 5/2 plus, and apart from this ground state there are various excited state. How can we explain this with the help of cell model? So now next question is, how can we justify these excited state of the nuclei? So for this we have come out of the assumption that the electron is moving independent of all other nuclei. So up to this point we were considering only individual nucleon. But if we come out of this, then we can explain the existence of these excited states. So here now in this video, I will discuss 3 or 4 cases of different nuclei where I am going to explain you various cases of the excited state. We will try to find out the region of the existence of these excited states. So we are starting with this example of this nuclei 8O17. So 8O17, 8 is the atomic number of proton will be 8 and automatically number of neutron will be 9. So here we have two numbers, proton number is 8 and neutron number is 9. Here in case of protons, all the protons are paired up. So they will not contribute to the angular momentum here. So we are going to consider this 9 number, which is the number of neutrons in the nuclei. So we are considering this number of neutrons. So N number is 9, neutron number is 9. So first what we are going to do here, we will write the energy level sequence. How these neutrons are filled in different energy levels or different energy cells. So first level will be 1s 1/2, so 2 will be here. After this energy level will be 1p 3/2, so 4 will be here. Then we have 1p 1/2, 2 will be here. After this we will have 1d 5/2 and last neutron will be here. So unpaired neutron is here in this cell, 1d 5/2 cell. Basically last neutron exists. I have also written the next two sublevels 2s 1/2 and 1d 3/2. In general there is no neutron in these sublevels, so I have written here 0. So here I have written 0, it means there is no neutron here in these two cells, subcells. So first question arises, how we will find out its ground state? So first, ground state. How we will justify the ground state? How will you justify the ground state? So basically for the ground state, we will check the unpaired neutron. We will find out the cell in which unpaired neutron exists. So unpaired neutron exists in 1d 5/2. J value for this 1d cell is 5/2. So here you will write that J will be 5/2 here. J will be 5/2 here. Now what will be the parity? Parity pi. Pi will be equal to minus 1 to the power L. So SPD, this will be minus 1 to the power 2. So this will be even parity. This will be a plus 1. So it will be the even parity. So ground state will have even parity. So we will write it as J pi and this will be phi by 2 plus. So in this way, we have explained this ground state with the help of cell model. Now, we come to other excited states. How we will justify the other excited states? So first, number two, suppose we are providing some external energy, or some external energy is captured by this nuclei, or this nuclei has some external energy, and as a result of this external energy, in the influence of this external energy or photon, basically if this neutron which is here in 1d by phi by 2, if it jumps from here to here, so if some external energy is provided and under the influence of this external energy, if unpaired neutron in 1d phi by 2, so unpaired neutron which is here in 1d phi by 2, if it jumps from here into 2s 1 by 2. So this unpaired neutron is excited to the next energy subcell. So here in 1d phi by 2, number of neutron will become 0, and in this 2s 1 by 2. I have not written these three. I am just writing here these two because they are involved in this transition. So unpaired neutron moves from 1d to 2s subcell, and now unpaired neutron exists in 2s 1 by 2 subcell. What is the J value of this? J value of this is 1 by 2. J value is 1 by 2 here. What will be the parity? Parity will be equal to minus 1 to the power L. So for S subcell, L value will be equal to 0. So I am going to write here 0 minus 1 to the power 0 is equal to plus 1. So it will have even parity. So it will be 1 by 2 plus. So due to the transition of this unpaired neutron from 1d subcell to 2s subcell, energy subcell, this excited state comes into the picture. So if we are providing so much amount of energy, the difference between energy equal to the difference between these two to this unpaired neutron, then automatically the unpaired neutron which was here, it will jump to this, and this new combination of neutron, this new configuration of neutron will form the excited state that is represented by 1 by 2 plus. So in this way, we have explained this energy level. Now, come to the next excited state. So third type of excited state. This will come into the picture if one of the neutron which is here in 1p3 by 2, if it jumps from here to 1d phi by 2, then next excited state will come into the picture. So what I am saying, if energy level will be like this, 1s 1 by 2, it will be 2 here, and this will be 1p 3 by 2, it will be 4 here, 1p 1 by 2, 2 here, and it is 1d 5 by 2. This is the energy sequence up to this point. If one of the pair breaks here we have two pairs of neutrons. If one of the pair breaks and one of the neutron jumps from here to here, so one of the neutron jumps from 1p state to 1d state, 1p 3 by 2 state to 1d 3 by 2 state, then what will happen? Here number will become 3 and here number will become 2. So after this transition, this will be the situation. So when a pair is broken here we have two pairs, one of the pair breaks, and out of this broken pair, one of the neutron jumps to 1d phi by 2, then it will give rise to an excited state. Now, where will be the unpaired neutron? Unpaired neutron will be here. So what will be the excited state corresponding to this? This will be J, its J will be 3 by 2. Its J will be 3 by 2. What will be its parity? Its parity, so its parity pi will be equal to minus 1 to the power 1. So this will be minus 1, or this will be the odd parity. Odd parity. So this will be 3 by 2 minus. So in this way, we have obtained the another excited state. So this excited state 3 by 2 minus, this is its existence lies in the fact that if one of the neutron from 1p 3 by 2 jumps to 1d phi by 2, then here unpaired neutron will be here, and as a result, what we are going to find out? We are going to find out the next excited state 3 by 2 minus. So in this way, we can explain the excited state 3 by 2 minus. So this is here, this is odd parity. So you have obtained this 3 by 2 minus. So up to this point in this example, we have already find out the ground state as well as two excited state. Here I just want to mention you one thing. When you are breaking a pair of proton or pair of neutron, then in the breaking of this pair, energy required will be roughly 2 MeV. Roughly 2 MeV energy is always required to break the pair of protons or neutrons inside the nuclei. So you have to remember this fact. Now, come to the another case. Suppose next excited state. How can you find out next excited state? So if suppose here in 1p 1 by 2 we have a pair of neutrons. So if this pair breaks and one of the neutron jumps from 1p 1 by 2 to 1d phi by 2, then here number of protons will be 2, so they will be paired up, and unpaired will be here in 1p 1 by 2. So another excited state you can observe if one of the proton in 1p 1 by 2. So here initially it has 2 protons, and this 1d phi by 2, this sublevel has 1. If this pair breaks and it jumps from here to here, then number of protons here it will become 1, and here it will be 2. Now they are paired up, and this is unpaired one. This unpaired one will be responsible for the angular momentum spin. So what will be the angular momentum spin here? This will be J equal to 1 by 2. What is the value of J here? This is 1 by 2. So J will be equal to 1 by 2. What will be the parity? This is the P subcell. For P, L is equal to 1. So automatically this will be minus 1 to the power 1. So this will be a minus 1. This will be a odd parity. So parity will be 1 by 2 minus 1. Parity here is basically minus 1 to the power 1. So this was equal to odd parity. So in this way we can explain this 1 by 2 minus state. So in this way we have explained the existence of this 1 by 2 minus state. Now we are left with two other excited states. So we will focus on these two excited states. How can we get these two excited states? So next is fifth one. How can we obtain the next another excited state? What type of transition will be required? If one of the neutron which is here, which is one unpaired neutron which is here, if it jumps from here to here, then we can get this 3 by 2 plus excited state. So from this configuration we can observe that we want to find out that 3 by 2 plus. How can you find 3 by 2 plus? Only if one unpaired neutron which is here, if it jumps to 1d3 by 2, if it jumps to 1d3 by 2, only then we can get this one. So this transition will take place like this, 1d 5 by 2, so this is the fifth one, 1d 5 by 2, and here we have one neutron. After this we have 2s 1 by 2 0, and there is no neutron here. There is no neutron in 1d3 by 2. So 0 is here. If this unpaired neutron jumps from here to here, then it will become 0 and it will become 1. Now unpaired neutron will be in 3 by 2 state. Now unpaired neutron will be in 3 by 2. 1d3 by 2 state. So what will be its J value? J value will be 3 by 2. So this is unpaired. Electron is here. So J will be 3 by 2. What will be the parity? Parity will be equal to minus 1 to the power L. What is the value of L for D? SPD. So it will be 2. L value is 2. So this is plus 1. So parity is even parity. So we can write that the angular momentum, spin and parity of this excited state will be 3 by 2 plus. 3 by 2 plus here. So this 3 by 2 plus excited state can be obtained in this way. This is another method by which one can obtain the excited state. Now, last excited state is 5 by 2. 5 by 2 minus. 5 by 2 minus. Now, how can you obtain this 5 by 2? So basically 5 by 2 is not here in picture. There is, here we have one 5 by 2, but when unpaired neutron is here, we will get this will be responsible for the ground state. So I'm not finding any way in which we can explain this 5 by 2 minus. So for this, what is explained here, how this excited state was explained, the way for this is like here, 1p 3 by 2, this will be 4, 1p 1 by 2, this will be 2, 1d 5 by 2, this will be 1, and this will be 2s 1 by 2. This is the situation right now. Right now, we have this situation. If this paired neutron breaks, if this pair of neutrons breaks, and one of the neutron jumps to 2s 1 by 2, if first pair will break and then out of this pair one of the neutron will jump to 2s 1 by 2, then our situation will be like this. Here we will have 1 and here we will have 1. So now we have 3 unpaired neutron. Now we have 3 unpaired neutron and we have to explain this state 5 by 2 minus. So to explain this state, these scientists who were working in the field of the cell model development, basically they come out of the assumption that this electron, each and every electron moves individually or independently of other nucleons inside the nuclei. So what they were saying that, okay, up to this point we have explained ground state with the help of this unpaired single electron, single proton or neutron, not electron, sorry. But they were saying if we have to explain these excited state, then we have to widen the scope of the cell model. Now they come to the conclusion that not only one unpaired neutron or proton, rather more than one unpaired neutron or proton can participate for the development of the excited state, in the formation of the excited state. So what they were saying that here, these 3 unpaired neutron will participate in the formation of 5 by 2. So what are the possibilities here? What will be the J value? Here we have 3 J values. 1 by 2 plus 1 by 2. This second is 5 by 2. And this will be 1 by 2. So these three neutrons these three neutrons which are not equivalent. These are not, you have to remember, these are not equivalent. These are not equivalent neutrons. They participate, they combine together and form this 5 by 2 minus state. So what are their J values? 1 by 2 plus 5 by 2 plus 1 by 2. So if this and this, they become antiparallel to each other, so they can cancel out, and we can get 5 by 2. We can have J value. Other values are also possible. With this combination, you can find out many values, but here we are interested in 5 by 2. How will you get 5 by 2? If this one and this one, they become antiparallel to each other, then surely our J value will be 5 by 2. So this J value is 5 by 2. This can be explained in the way that more than one unpaired neutron are participating together to form this state, this excited state. And here, what is important? Important is they are not equivalent neutrons. Their J values are different, their L values are different. Okay? They are equivalent electrons. If you have two neutrons here, then these two neutrons will be equivalent. But here, this is present in this subcell, in this 1p 1 by 2 subcell. Here, another is present in 1d 5 by 2. Another, they are present in different subcells. So they are not equivalent neutrons. So J value is 5 by 2 here. Now, what will be the parity of this excited state? Now, parity of this excited state will be minus 1 to the power L1 minus 1 to the power L2. This is a multiplicative nature. Parity has multiplicative nature. So this will be, so here three neutrons, unpaired neutrons are participating. So the parity of the final state of this excited state will be given by this. So this will be minus 1 to the power L1. What is the value of L for this P? This is 1. Minus 1 to the power D, SPD, so this will be 2. And here this will be minus 1 to the power, for S it will be 0. So this will be minus 1, or this will have odd parity. So this excited state will be represented by J pi, and J pi will be equal to 5 by 2 minus. So in this way we have explained all these possible excited states. So in this way, we have explained all these possible excited states which are present in 8O17 nuclei. So now come to another example. And this example is of argon nuclei. So this is 18 Ar38 nuclei. Number of proton is 18. Number of neutron is 20. So here, this is the ground state of this argon 38 nuclei, and these are the excited states. Now we have to explain these excited states. We want to find out the ground state as well as these excited states. So how can you explain the ground state? Basically, this is a even nuclei. Number of proton is even, number of neutron is even. So number one, ground state. So this nuclei is even nuclei. So this nuclei is even nuclei. So automatically its ground state will be given by J will be 0, parity will be positive. So this will be equal to 0 positive. This will be the ground state, angular momentum spin, and parity. This is for the ground state. So for the ground state, spin and parity will be 0 plus. For every even nuclei, you are aware this ground state will be 0 plus. This is okay. Another excited states we can achieve by assuming the transitions of these protons or neutrons from lower sub-energy levels to higher sub-energy levels. So here number of proton is 18, number of neutron is 20. So you are aware about the magic number. Magic number are 2, 8, 20, like this. So 20 is a magic number. What I want to tell you here, this 20, this 20 number of neutron, this is a magic number. So it is more, this is a completely filled cell. This is representing completely filled cell neutron structure. So it is always very difficult to excite the neutron from one state, from one energy sublevel to another sub energy level, because this is exhibiting completely filled neutron structure. So automatically it is easier to move one of the proton whose number is 18 from the lower sub energy level to higher sub energy level. So it is easy. So we can consider one such thing like this. Here we can obtain one of the excited state if we consider that this pair of proton breaks up, and one of the proton will move from here to here. If we consider the shift of one of the proton from 1d 3/2 state to 1f 7/2 state, then we can obtain one of the excited state. So here what I am saying, that here in 1d 3/2 we will be left with 1, and here another proton will go to 1f 7/2. So one unpaired proton will be here, another unpaired proton will be here. So what will be the J value? How we will get the J value? This will be 3/2 plus 7/2 plus. Both these unpaired proton are in different cells, in different subcells. One is in D, another is in 1F. So basically they are not equivalent. So what J values we can obtain from this? So it will vary from J1 plus J2 to J1 minus J2. So what J values you can have? If you have two J values, suppose this is J1, this is J2, then we can have all J values. Resultant J values will be from J1 plus J2 to J1 minus J2 mode. So their values will lie from J1 minus J2 to J1 plus J2. So these values we can obtain by the combination of this J1 and J2. So we will use this formula. So from here, which values we can get? 7 minus 3, 4. So we can have 2, and this will be 5 here. So we can have 5. In between, there will be a difference of 1 in between J values. So these values will be 2, 3, 4, and 5. So these values of J are possible. If we are considering that one of the proton moves from here to here, then we will have two unpaired proton, and when these two unpaired protons combine together, then they will give us resultant J values, which will be equal to 2, 3, 4, and 5. Now what will be the parity here? What will be the parity here? Parity will be equal to minus 1 to the power L1. For D, what will the L value? Its L value will be 2, and here this will be minus 1 to the power L2. So L2 will be for F, S, P, D, F. So it will be 3. So this will be 3. L number for D is 2. L number for F is 3. So this will be minus 1 here. So this will be the odd parity. This represents the pi is equal to minus 1 represents the odd parity. So these states are possible. These are possible. It's not necessary that they are present, but these possibilities are there. So this state here we have 3 minus. So this 3 minus state is present here. So one can explain the presence of this 3 minus if one considers that this pair of proton breaks up and one of the proton jumps to next energy subcell 1f7/2, then we will have two unpaired proton, and these two unpaired proton will give us this state 3 minus. So in this way, one can explain this 3 minus state. One can explain this 3 minus state. Now, come to another excited states. How can we explain the other excited state? So if we consider that, we can explain another excited state if we consider that one of the proton jumps from here to here. So what we are saying that this pair of proton will break and one of the proton will move from here to here. One of the proton will move from 2s1 by 2 energy level to 1d3 by 2 energy level. So in case 3, if we consider this type of transition, 2s1 by 2 and 2 is here and this is 1d3 by 2, here we have 1. If one of the proton moves from here to here, then here it will reduce to 1 and this will increase to 3. This will increase to 3. Earlier, here 2 was here, 2 was here. So 1 moved from here to here. So here it will become 3. Here it will be left with 1. Now again we have 2 unpaired protons. One unpaired proton is here, another unpaired proton is here. So what will be the resultant J value? This will be the J value. These J values will be possible. 1 by 2 plus 3 by 2. So they can give us 3 by 2 minus 1. So this will be 1. And 3 by 2 plus 1 by 2. So this can be 2. They will provide us 2 values of J. So from here we can find out 2 J values. 2 J values are possible, 1 and 2. What will be the parity possible? What will be the possible parity? This will be minus 1 to the power L1. L for S is 0 and another unpaired one is here in 1d3 by 2. So this will be SPD. So this will be 2. L value for D subcell is 2. So this will be positive. This will be positive. So automatically pi will be even. Parity will be even. So which states are possible? So 1 plus and 2 plus. These 2 states are possible. Now we have 2. Here we have 2 plus state and this is 2 plus state. Now question arises, which one is this one? So here we are getting this 2 plus state if one of the proton jumps from 2s1 by 2 to 1d3 by 2. And we are getting this 2 plus state. But here in this diagram of energy levels for AR38, we have 2 plus and here again we have 2 plus. We have 2 energy states for which spin and parity is 2 plus. So which one is this one? So here what we have done, you have to consider one thing. Here we have broken a pair of protons. So for this we need roughly 2 MeV energy and then it has to jump from 2D S1 by 2 to 1D3 by 2. In 1D3 by 2 already all the protons are paired up. You are creating an unpaired one, so you need more energy. You need more energy. First you need energy for breaking the pair, then you will need energy for the shift of this proton from here to here. And again you need high energy because earlier all the protons were paired up and now we will have, after transition, we will have one unpaired. So basically always pairing is always favored, so you need higher energy. So automatically this is close to 2 and this 2 plus state is close to 2 MeV and this is much higher than this 2 plus state is corresponding to nearly 4 MeV. So for this transition we need energy much greater than 2. So automatically whatever the state we have get here 2 plus is surely this is 2 plus, this upper 2 plus state whose energy is closely equal to 4 MeV. Because here what is the concept here? Concept is very simple. In 2s1 by 2 we have 2 protons. So you have a pair of proton. You want to break this pair, so you need energy more than 2 MeV. So automatically you need more than 2 MeV energy, greater than 2 MeV energy. And then this proton will jump from here to here. Again you will need more energy. So automatically this energy should be somewhere here. So this 2 plus state is explained by this transition of the proton. Now, next question arises about this 2 plus excited state, from where 2 plus excited state is coming into the picture. So, if we consider this type of transitions of proton from one sublevel to another sublevel, and if we try all the combinations, then we don't find here in this type of transition, we don't find any transition with the help of which we can explain this 2 plus. So we cannot explain. So here I can write, we can't explain the existence of 2 plus state near 2 MeV energy right now. So whatever we have discussed up to this point, on the basis of that, we cannot explain this 2 plus state. But later on, we will find out that here this is an example of even nuclei. So in even nuclei, this is a even nuclei, and we have a level 2 plus which is close to 2 MeV energy, and we are not able to explain this. If you consider the excited state of another even nuclei, then you will again find out in every even nuclei you will find out a 2 plus energy state whose average energy you will find out is nearly 2 MeV, in between 2 MeV and 1 MeV. With every even nuclei you will find out this 2 plus state, and we are not able to explain the existence of this 2 plus state for even nuclei with the help of the discussion we have done up to this point. However, later on, we will modify this model, we will upgrade this cell model, and we will discuss vibrational energy levels. And on the basis of vibrational motion of the nuclei, one can explain this 2 plus state which exists in even nuclei. In every even nuclei, this 2 plus state is the first excited state. And this first excited state, 2 plus state in even nuclei, can only be explained later on with the help of vibrational model of the nuclei. So up to this point, we are not able to explain this. Later on, we will discuss this 2 plus state. We will explain this with the help of vibrational model. So we are able to explain these 2 states, but for this even nuclei, we are not able to explain this 2 plus state. So this was the second example. Hello students. In the last class, I have